And welcome back to another statics lecture. In today's lecture, we're going to cover the steps to draw a free body diagram, as well as introduce the equilibrium equations. Let's get started. Before we get started, I wanted to cover the drawing forces a little bit more. When drawing forces, there's this important concept to know, which is called the line of action. For a gravitational force, our line of action would look like this. And essentially what this line is this imaginary line on which the force acts upon. And the force can be drawn anywhere on this line of action. So again, for a gravitational force, we can draw it anywhere on this line of action. We can draw it going into the box, coming out of the box, inside the box. It's truly up to the engineer. The convention I always follow is drawing my forces coming out of the system. For a force kind of like this at a 45-degree angle, the line of action would look something like this, and that force could be drawn anywhere on that infinite line. The next thing I wanted to cover was the direction of your forces. Let's say you have a force and you don't really know which action it's directing upon. Well, you can use your engineering judgment and make your best guess, but luckily you don't really have to be correct. Let's say there's some force acting on this box in this direction, but we don't really know which way the force is acting out. Well, you can always just draw it in an arbitrary direction, and then whenever you solve your equilibrium equations, if you find out that you drew it in the wrong direction, you'll just have a magnitude that's negative, and that just means gotta flip the direction of your force. Alright, now let's cover the steps to draw a free body diagram. The first step to draw your free body diagram is to isolate each component in your system. The next step will be to define your coordinate system. The third step will be to draw all the forces acting upon each component. And finally, we're going to label each force. Okay, let's cover an example. In this example, we have a mass of m1, which is connected to a pulley, which is connected to another pulley, and is finally connected to a mass of m2. Our first step will be to isolate each component, so we'll get rid of the string connecting each of these components. Now, we're going to draw our coordinate system. Now it's time for the third step. Let's draw all of our forces. Since we have a mass, we know we have a gravitational force. So that will be going down. The gravitational force will also be pulling on the string connecting the mass to the pulley, which means we'll have a tension force pulling the mass back up. So we'll add that in here. Finally, let's label our forces. So we'll call this one gravitational force 1, and we'll call this tension force 1. Alright, pause the video now and see if you can draw the free body diagrams for the rest of the system. Alright, your free body diagram should look something like this. Now you may notice that I labeled both of these forces as tension force 1. That is because, due to Newton's laws, we know that these forces will be equal but opposite. And so they still will have the same magnitude, just opposite signs. Alright, let's get into our equilibrium equations. Our equilibrium equations come from Newton's second law, which says that the sum of forces acting on a system is equal to mass times acceleration. However, our systems are at equilibrium, which means acceleration is equal to 0. The next thing to note is that force is a vector with components force in the x direction, force in the y direction, and force in the z direction. Acceleration is also a vector with acceleration in the x direction, acceleration in the y direction, and acceleration in the z direction. However, since this is equal to 0, it'll also be equal to our 0 vector. That means that Newton's second law can be rewritten as the sum of forces in the x direction is equal to 0, the sum of forces in the y direction is equal to 0, and the sum of forces in the z direction is equal to 0. And those are equilibrium equations. Engineers will typically use this form as it makes our lives a little bit easier when dealing with vectors. Now let's cover an example. In this example, we have a mass of m which is sitting on a ramp at angle theta. The mass is held up using a string. The reason why I chose this case is because it brings up the important question of defining your coordinate system and how different definitions of your coordinate system can make your life a little bit easier or a little bit harder. There are two different ways to define this coordinate system. One is with the x direction aligned with the horizontal direction. The other option is to align the x direction with the ramp. I will cover both of these cases, and you'll see why an engineer might choose one over the other. Let's get started. For our first scenario, we're going to align the x direction with the ramp, like so. Let's draw the free body diagram. First force we'll draw is our gravitational force. Then we'll draw our normal force coming out of this box. And finally, let's add in our tension force. Can't forget to label them. Now we can begin writing our equilibrium equations. Let's start with the sum of forces in the x direction. Now, when looking at these forces, we see that the normal force is fully aligned with the positive y direction, so we don't need to write that here. Our tension force is fully in the x direction and it's positive, so we'll add that in here. So we'll have positive tension force. Now, let's look at our gravitational force. What we can see is both partially in the y and x direction, which means there will be a component in the y direction and a component in the x direction. Now we should solve to find out what each of these magnitudes would be. Let's redraw our triangle over here. So there is our gravitational force. This will be our y component, and this will be our x component. Now, the y component and the x component will always be at a 90-degree angle from each other. The other thing we know is from the horizontal axis, this angle will be theta, which means we can define this as an arbitrary angle alpha. And the gravitational force and the horizontal axis will be at a 90-degree angle from each other, which means we can say that alpha plus theta is equal to 90. We can also rewrite that as alpha is equal to 90 minus theta. Now we can begin to draw out or write out our equations. I'll just label these real quick. Now, from trigonometry, we can deduce that the gravitational force in the x direction will be equal to the gravitational force cosine alpha. And we can also figure out that the gravitational force in the y direction will be equal to the gravitational force sine alpha. Okay, you may not be familiar with this idea. However, cosine of 90 minus theta is actually just equal to sine of theta. And sine of 90 minus theta is equal to cosine of theta. So we can rewrite this as the gravitational force times sine of theta, and we can rewrite this as the gravitational force cosine of theta. All right, now we should be able to figure out the rest of the problem. So we see that the gravitational force in the x direction is in the negative x direction, and its value will be the gravitational force sine theta. So we'll write negative gravitational force sine theta is equal to 0. Now we can do the equilibrium equation in the y direction. Say sum of forces in the y is equal to the normal force, which is fully in the positive y direction, minus the gravitational force cosine of theta, which is also equal to 0. Now let's say in this equation we want to define the tension force as some function of the gravitational force. Well, it'll be pretty easy. We would see that the tension force will be equal to the gravitational force sine of theta. Now let's cover the other case where we define our coordinate system where the x direction aligns with the horizontal axis. Our free body diagram would still look the same. However, when we go to start writing our equilibrium equations, we'll see that both the tension force and the normal force will have components in the x and y direction. All right, for the tension force, it's pretty simple. This angle we know is theta. And so we can write this as the tension force in the x direction is equal to the tension force times cosine of theta. And we can rewrite this as the tension force in the y is equal to the tension force sine of theta. To solve for the normal force, it's going to be a lot like our normal force in the previous example. We know that the x and y are going to make a 90-degree angle, and we know that the angle between the mass and the normal force in x is going to be theta, and that's due to the law of interior angles, which means we can do the same step of defining an arbitrary angle, and we'll call this one beta. And theta plus beta will be equal to 90, which means that beta is equal to 90 minus theta. We can follow all the same steps we did in the previous example, and we'll see that the normal force in the x direction will be equal to the normal force sine theta, and that our normal force in the y direction will be equal to the normal force cosine of theta. Now we're ready to finish writing out our equilibrium equations. We'll see that sum of force in the x direction, our tension force in the x direction is fully in the positive, so we'll write that with the positive sign, cosine of theta. However, our normal force in the x direction is purely in the negative, so we'll say minus normal force sine of theta is equal to 0. Similar process for our equilibrium equation in the y direction. We'll see that our tension force has a positive direction, so we'll say positive tension force sine of theta, and we'll also see that our normal force is in the positive direction, so we'll say plus the normal force cosine of theta. And then finally, our gravitational force, which is purely in the negative. So we'll say minus the gravitational force is equal to 0. Now, if we were trying to find the tension force as a function of the gravitational force, again, there's a lot more steps to actually do it. The first thing is we'll take our equilibrium equation in the x direction and rewrite it as the normal force times sine of theta is equal to our tension force cosine of theta. If we divide both sides by sine of theta, we will get the normal force is equal to our tension force cosine of theta over sine of theta. And we plug this value in to our equilibrium equations in the y direction right here. What we'll get is that our tension force sine of theta plus our tension force cosine of theta sine of theta times cosine of theta minus our gravitational force will be equal to 0. All right, that means that this can also be rewritten as times sine of theta plus ft cosine squared of theta over sine of theta minus our gravitational force is equal to 0. Now, let's multiply both sides by sine of theta. What we'll get is the tension force sine squared of theta plus the tension force cosine squared of theta minus the gravitational force sine of theta is equal to 0. We can rewrite it a little bit more. If we factor the tension force out of this, we'll get our tension force times sine squared of theta plus cosine squared of theta is equal to our gravitational force sine of theta. This identity here is actually just equal to 1. So finally we'll get our answer, which our tension force is equal to our gravitational force sine of theta. And that's exactly what we got in the previous problem, which is a lot less math.